Hello everyone, welcome to this lesson. We are starting with network fundamentals and one of the most important concepts in networking, TCP/IP. Before we go deeper into technical details, I want you to understand the bigger picture because if you understand the logic behind networking, everything else becomes much easier to learn. Networking is not only about cables, routers, or switches. It's not just about connecting devices physically. At its core, networking is about communication between devices. It's about how one device creates data, how that data is sent across the network, how another device receives it, and how it understands and processes that data correctly. Now think about how complex this really is. Different devices use different types of hardware. Some devices use fiber optic cables, another use Cooper cables, and many use wireless technologies like Wi-Fi. These technologies work in very different ways. They use different signals, different speeds, and different transmission methods. But despite all these differences, communication must still work correctly and reliably. A device sending data should be confident that the data will reach the destination, and the receiving device should be able to understand that data without confusion. So, how is this possible? The answer is standardization. In networking, we use standards and protocols. Standards define how technologies should work, and the protocols define how communication should happen. Protocols specify how data is formatted, how it is sent, how it is received, and how errors are handled. Without these standards and protocols, each device would behave differently, and communication between devices would simply not be possible. In this lesson, our goal is to build a strong foundation. We will not just memorize concepts, we'll understand how everything fits together. Step by step, you will start to see how data moves through a network, how different layers interact, and how communication is achieved in real world environments. And once you understand this foundation, learning more advanced the networking topics will become much easier. Now let's talk about networking models. As we mentioned before, networks rely on standards and protocols to function correctly. Protocols define how communication happens, how data is created, how data is sent, received, and interpreted. But here is a challenge. In real network, there are not just a few protocols. There are many protocols. Each protocol is responsible for a different function. Some handle web communication, some of them handle data delivery, another handle addressing, and other handle error control. Now imagine trying to understand all these protocols without any structure or organization. It would be very confusing for you. You wouldn't know where one process starts and another ends, and it would be very difficult to design or troubleshoot networks. That's exactly why networking models exist. A networking model provides a structured way to organize all these protocols into layers. Each layer represents a specific part of the communication process, and each layer has a clearly defined responsibility. For example, one layer focuses on how data is presented to application, another focuses on how data is delivered reliably, and another focuses on how data is routed across networks. In this layered approach is very powerful because it separates complex processes into smaller, manageable parts. You can focus on one layer at a time without needing to understand everything at once. Now, Let's go back to a simple analogy. Think about building a house. Imagine that you are building a house. You don't start to build everything at once. You first create a plan, blueprint. It shows where the foundation is, where the walls go, and how the electrical system works, and how everything connects together. Networking models work in the same way as well. So they provide a clear structure. They defines how communication should happen step by step. Everything is planned, structured, and organized, and this brings major advantage. First, it makes networks easier to design. Engineers can focus on specific layers when building systems. Second, it makes networking easier to understand. Instead of dealing with everything at once, you learn layer by layer. And third one, very important, it makes troubleshooting much easier. If something goes wrong, you don't check everything blindly. You isolate your problem. You identify which layer is causing the issue, and you focus only on that part. So networking models are not just theoretical concepts. They are practical tools that help us to build, understand, and manage real-world networks more efficiently. We need to focus on TCP/IP. Today, TCP/IP is the most widely used networking model in the world. But to really understand its importance, let's connect it to your everyday experience. Almost every device you use support TCP/IP, whether you are using a smartphone, a laptop, a server in a data center, or even smart devices like TVs and IoT devices, they all rely on TCP/IP to communicate. Now think about what you do every day. You open a website, you send message, and you watch videos online. You connect at different services. All of these actions involve sending and receiving data, and all of that data follows the rules defined by TCP/IP. Even the internet itself is built on this model. This means every piece of data, every website, every email, every video travel using TCP/IP. Now, here is something very important. The devices in a network are not the same. They are built by different companies, they run different operating systems, and they are located in different parts of the world. Despite all these differences, they can still communicate smoothly. Why? Because they all follow the same standard, TCP/IP. You can think of TCP/IP as a common language, just like people from different countries can communicate if they speak the same language. Devices can communicate because they all understand TCP/IP. Now let's go a bit deeper. TCP/IP is not just one protocol. It is a combination of protocols working together. For example, TCP is responsible for reliable data delivery. It makes sure that data arrives correctly and in the right order. IP is responsible for addressing and routing. It ensures that data knows where to go. Together, they create a complete communication system. And this is exactly why TCP is so powerful. It is flexible, scalable, and reliable. It works in small networks and in massive global networks like the internet. That's why in CCNA, TCP/IP is a core topic, because CCNA is not just about theory, it is about real-world networking. If you truly understand TCP/IP, you are not just memorizing concepts for an exam. You are learning how data actually moves across networks, how devices communicate in real environments, and how modern networks operate. And this knowledge is something you will use in real jobs, real systems, and real scenarios. So as we move forward, keep this in mind. Understanding TCP/IP means understanding the foundation of networking itself. To make communication easier to understand, TCP/IP is divided into four layers. Each layer has a specific role, and each one is responsible for a different part of the communication process. Let's briefly go through each of them. First, we have the application layer. This is the layer closest to the user. It provides network services to applications like web browsers, email clients, and messaging applications. Protocols like HTTP, HTTPS, and DNS operate at this layer. In simple terms, this is where communication starts from the user perspective. Next layer is the transport layer. This layer is responsible for end-to-end communication between devices. It ensures that data is delivered correctly in the right order and without errors. Protocols like TCP and UDP work at this layer. So this layer focuses on reliability and data delivery. Then we have the network layer. This layer is responsible for logical addressing and routing. It uses IP addresses to identify devices and decides how data moves from the source to the destination. Routers operate at this layer. You can think of it as the layer that finds the path for the data. And finally, we have the data link and physical layers. These layers handle the actual transmission of data. The physical layer deals with cables, signals, and hardware. The data link layer defines how data is formatted and sent over the network using things like MAC addresses. Together, these layers ensure that data is physically delivered from one device to another device. Now let's understand the application layer with a simple example. Imagine you open your browser and type a website address. You press enter and the page loads. It looks very simple, right? But in the background, your browser is actually sending a request. It uses a protocol called HTTP. This request is basically saying, please send me this web page. The server receives this request and sends back a response. If everything is okay, you will receive your web page, and it means that you receive 200 OK code from server, and the page opens. If the page doesn't exist, you will see the code 404 not found. This process is called the request response model, and it is one of the most common ways devices communicate on the internet. Now, here is the key idea. The application layer is a layer you interact with. When you use a browser, send an email, or open an application, you are using the application layer. The technical details happen in the background, but from your perspective, everything feels simple. So the next layer is transport layer. This layer is responsible for communication between devices from end to end. Its main job is to make sure that data is delivered properly from one application to another. When data is sent across a network, it's not sent all at once. Instead, it's divided into smaller pieces called segments. This makes transmission more efficient and easier to manage. Now, during transmission, some problems can happen. Some segments can be delayed, arrive out of order, or even get lost. This is where the transport layer becomes very important. At this layer, we mainly use two protocols, TCP and UDP. Let's start to understand TCP first. TCP stands for Transport Control Protocol. It is designed to provide reliable communication. TCP keeps track of all the segments that are sent. The receiver sends acknowledgement back to the sender to confirm that data was received correctly. If a segment is missing, the receiver detects the gap and requests that specific segment again. When the sender retransmits the missing data, this process is called error recovery. TCP also ensures that data arrives in the correct order even if it was sent in multiple segments. Because of all these mechanisms, TCP is considered reliable. But this reliability comes with a cost. It can be slower due to extra checks and control. So another protocol in this layer is UDP, which stands for User Datagram Protocol. Unlike TCP, UDP is much simpler. It doesn't guarantee delivery. It doesn't check for errors, and it doesn't retransmit lost data. It simply sends the data and doesn't wait for a response. This makes UDP much faster than TCP, but it is less reliable. So where we need to use UDP, why we need UDP? UDP is used in applications where speed is more important than perfect accuracy. For example, live video streaming, online gaming, voice calls, etc. In these cases, a small data loss is acceptable, but delays are not acceptable. So, TCP, reliable, ordered, slower. UDP is faster, simpler, less reliable. Understanding the difference between these two protocols is very important for CCNA and real-world networking. In the next lessons, we'll explore them in even more detail. Now we need to understand how layers communicate with each other. So far, we said that networking models divide communication into layers. But an important question is this. How do these layers actually interact with each other? There are two main types of interaction with networking. The first one is called same layer interaction. This happens between the same layer on two different devices. For example, the transport layer on your computer communicates with the transport layer on a server. Even though the data travels through many layers and devices, logically, the communication is happening between the same layers. How does it work? Each layer uses specific protocols and headers. For example, the transport layer uses TCP or UDP. This protocol defines how the data should be formatted and understood. So when the sender sends data, it adds a header that contains important information. Once the receiver gets the data, the same layer reads that header and understands how to process it. This is why it is called the same layer communication, because both sides are using the same rules. Second type is adjacent layer interaction. This happens inside the same device. Each layer does not work alone. It depends on the layer below it to perform certain tasks. For example, the application layer creates data and passes it to the transport layer. The transport layer processes it and passes it to the network layer. The network layer then passes it to the data link layer, and finally to the physical layer for transmission. So each layer provides services to the layer above it and uses services from the layer below it. This is what we call adjacent layer interaction. Now here is a key idea you should remember. Same layer interaction is logical communication between layers on different devices. Adjacent layer interaction is actually communication between layers inside the same layer, the same device. This structured approach makes communication organized, predictable, and scalable. It allows each layer to focus on its own job without needing to understand all the details of other layers. And this is one of the main reasons why networking models are so powerful and widely used. Now we come to the network layer. This is one of the most important layers in networking. This is where IP or Internet Protocol works. The main job of this layer is to make sure that data goes from the source device to the correct destination. For this, every device in a network is assigned an IP address. You can think of an IP address like a home address, just like a letter needs a correct address to reach the right house. Data also needs an IP address to reach the correct device. So when data is sent, the network layer adds source and destination IP addresses to it. This information helps the network understand where the data is coming from and where it needs to go. Now, in most cases, devices are not directly connected to each other. Data needs to travel through multiple networks. This is where routers come in. Routers are devices that connect different networks together. Their job is to forward data from one network to another network. When a router receives data, it looks at the destination IP address. Based on that address, it decides where to send the data next. It doesn't always know the full path to the destination. Instead, it makes a decision step by step, sending the data to the next best location. This process continues until the data reaches its final destination. This is called routing. A simple way to understand this is to think of routers like post offices. A post office receives a letter, checks the address, and sends it to the next post office closer to the destination. The letter moves step by step until it finally reaches the correct address. In the same way, routers forward data across networks until it reaches the correct device. So, network layer is responsible for addressing and routing, and it plays a key role in enabling communication across different networks, including the internet. The next layer is data link layer. So far, we talked about how data is created, organized, and routed. But now the question is, how does data physically move from one device to another? This is where data link layer and the physical layer comes in. Let's start with the physical layer. The physical layer is the lowest layer in the model. It deals with the real physical components of the network. This includes cables like copper and fiber, connectors, network interface cards, and even wireless signals like Wi-Fi. At this layer, data is not seen as packets or segments. It is simply a stream of bits, zeros, and ones. The physical layer is responsible for transmitting these bits as electrical signals, light signals, or radio waves. Now let's move one level up, the data link layer. The data link layer works closely with the physical layer. Its job is to prepare data for transmission over the physical medium. It takes packets from the network layer and converts them into frames. This process is important because frames contain additional information needed for communication within a local network. One of the most important things the data link layer uses is the MAC addresses. A MAC address is a unique identifier assigned to each network interface. While IP addresses are used for communication between networks, MAC addresses are used for communication inside a local network. So when devices are connected to the same network, they use MAC addresses to identify each other. The data link layer also helps detect errors in transmission and ensures that data is delivered correctly within the local network. Now, here's a key idea. The physical layer handles how data is transmitted as signals, and the data link layer handles how data is formatted and delivered locally. Together, these layers are responsible for the actual movement of data from one device to another device. Without these layers, all the higher level logic we discussed early would not work. Finally, let's talk about encapsulation. Encapsulation is one of the most important concepts in networking. It explains how data is prepared and packaged as it moves through different layers before being sent over the network. Let's understand this step by step. When data is created at the application layer, it is just raw data, for example, a web request or a message. As this data moves down through the layers, each layer adds its own information to it. This information is called a header. Each header contains specific details that help the next layer understand how to handle the data. Now let's follow the process. At the transport layer, a header is added that includes things like port numbers and sequence information. At this point, the data is called a segment. Then the data moves to the network layer. Here, another header is added. This header includes the source and destination IP addresses. Now, the data is called a packet. Next, the data goes to the data link layer. This layer adds its own header and also a trailer. This includes MAC addresses and error checking information. At this stage, the data is called frame. Finally, the frame is sent through the physical layer as bits over cables or wireless signals. This entire process, adding headers at each layer, is called encapsulation. Now let's look at what happens at the destination. When the data reaches the receiving device, the process happens in reverse. Each layer removes its own header and passes the remaining data to the next layer. This is called the encapsulation process. So the data is gradually unpacked until it reaches the application layer, where it can be used by the user or the application. A simple way to understand this is to think of sending a package. You put an item in a box, add labels, and maybe you put it inside another package. At the destination, each layer of packaging is removed until the original item is revealed. This is exactly how encapsulation works in networking. And this step-by-step process is how data travels reliably across networks. So now you have a basic understanding of how TCP/IP works. At first, it may seem a little complex, but you don't need to worry. Step by step, it will become much easier. In the next lessons, we'll go deeper into each part and understand everything in a simple and practical way. If you want to really learn networking and prepare for the CCNA exam, make sure you follow the course step by step. And if you find this lesson helpful, don't forget to subscribe to the channel so you don't miss the next videos in this series. Let's continue in the next lesson.